In this video, we're going to take a look at the implementation of a BCD adder, an n-digit BCD adder, in Verilog, and how to test it using different types of test benches. BCD stands for binary coded decimal, and BCD digits are 4-bit numbers in the range from 0 to 000 to 001, 0010, etc., up to 1001, corresponding, of course, in decimal to 0 and 1 and 2 all the way up to 9. The block diagram of a BCD adder, which is typically made from regular binary 4-bit adders, looks like this. So we have an input here, X, so this is a 4-bit input, and another 4-bit input Y, and a carry in, and we use regular binary addition. So what can happen is that this intermediate result R here can be another BCD number, assuming that X and Y are BCD. Okay, so we assume that those are BCD numbers at the input. So R3 might be another BCD number. For example, if we add 2 plus 3, we get 5. And that would still be in the range of BCD numbers. But if we take 5 plus 7, for example, we get 12. So if we had 0, 1, 0, 1 here for 5 and 0, 1, for 7, then we get 12 here. That's 1, 1, 0, 0. And that's not the BCD number anymore. And so we have to apply a correction factor. And what we do is we generally check whether R3 down to R0, the result of this addition, plus the carryout, which makes a fifth bit, whether this R is greater than 9 or not. And if it is greater than 9, then we have to apply a correction. So in the case, for example, of the 12 here, the correction is that we have to add 6 to it. So we had 6, 0, 1, 1, 0, which is 6, and then we get 0, 1, 1 and 1 is 0, keep a 1, 1 and 1 is 0, keep a 1. And so what we're getting is a carry out, so that would go out here, and 0, 0, 1, 0. So now we actually have 12 in BCD representation. The topmost bit here just means 0, 0, 1, or 0, 0, 0, 1, and the lower 4 bits is the ones digit of this addition. So what we do here in the block diagram is if we detect that R is greater than 9, we switch, with that multiplexer, we switch the input of that second regular binary adder so that the input becomes 6, and we add 6 to the previous result that we did from the first adder. And if the result stays within the range between 0 and 9, then we just switch that to an input of 0, and we add just 0 to it, and actually just simply make the S equal to R at the output. And in the case where we apply the correction, then we know that there's going to be a carryout, so we set the carryout equal to 1. In Verilog, we start with a 1-digit BCD adder, which is actually the picture that we just saw in the block diagram above. And then we will use that 1-digit BCD adder n times in order to make an n-digit BCD adder. So we have a carry input, we have an input X, an input Y, and an output S, which is going to be the sum. All of those are assumed to be in BCD format. And the carry out we have as well. We declare the inputs and the outputs. The outputs we declare to be registers because the way we implement this is by using a procedural always block, and whatever is being computed in that always block has to be stored in a register rather than going to a wire. And we have 4-bit quantities for X, Y, and S, so we go from 3 down to 0 for X and Y, and from 3 down to 0 for S. The carry in and carry out, those are just single bits. And then we need an intermediate result, or we need a register for the intermediate result R. And that's declared here, another 4-bit register. Okay, so the sensitivity list here in the always after the always keyword is C in X and Y. If any of those change, then we have to do the computation. And we just use an arithmetic statement here and use the built-in addition in Verilog. So we take X plus Y plus C in, and we produce a 2-bit output here, or actually it's not bits, it's 5 bits altogether. It's 4 bits for X, 4 bits for Y, but C in is a 1-bit quantity. So normally that would make a 4-bit sum, but because we declare this here with the concatenation as a 5-bit result, Verilog will compute this with a 5-bit result, and in this way we get the carryout from that first addition. And if that carryout is 1, or if R is greater than 9, then we know that we have to apply the correction factor. So we add now 6 to R, and that becomes S, the output. And the carryout, we know in this case, has to be equal to 1. So we set that to 1. And with this command here, that gives us just a 1-bit 1. And then the else clause, if we neither have a carryout nor have an intermediate result greater than 9, then what we actually computed with the first adder is already the result, and so we just make the output S equal to R, that output of that first adder. So now we want to test that this 1-digit BCD adder is indeed doing the right thing. So we set up a clock here, a register for the clock. And further down here, we will set clock equal to 1. And then we will also here use an always statement and 5 units of time delay. And because we set the time scale to 1 nanosecond, that corresponds to 5 nanoseconds time delay. The clock will toggle between the values of 0 and 1 every 5 nanoseconds. So we get the clock period of 10 nanoseconds. And then we can use that clock to increment the counter. The counter is defined here. It's a register, 8 bits. Actually 9 bits. It goes from 8 to 0. We need 8 bits for the X and the Y input. Each of those has 4 bits. But we also need an additional bit for the carry in. So that's why we made this 9 bits wide. And then we need to declare wires for the input X, Y, and the output S for the actual module that we want to test. And we also have carry in and carry out. Those are just single bit wires. So we initialize the clock to 1, and we initialize the count to -1. So that's the value that we want to have before time 0. What it means is that at time 0, clock will go to 0, and count will go to all zeros in that register that we have set up for it. So the clock is running through this always command here, and then the next always command is the one where we increment the counter. So at every positive edge of the clock, we run through this procedural statement, and we increment the count by 1. Now, because this is a binary count, what can happen is that we go 0, 1, 2, 3 up to 9, and then the next thing is going to be 10. And 10 is not the legal input. 10 meaning 1, 0, 1, 0 is not the legal input in BCD. And so we look at what the value of count is after incrementing by 1. And if the lower 4 bits that we are using, that's bits 4 down to 1, if those are greater than 9, then we add 12 to that to compensate and bring this back to 0 again. And if the upper 4 bits of the count are greater than 9, then we just set the count back to 0, because then we have reached the end of one counting cycle and we start a new counting cycle. You notice here that the the lower 4 bits that we are using are going from 4 to 1, but there's also bit 0. Bit 0 is what we actually use for the carry-in, so that we test our digit BCD adder both with the carry-in of 0 and the carry-in of 1. And then the next step is to actually use now the output of that counter to go into the module under test, the MUT here, the add BCD digit. So we have here C in, X, Y, S, C out, as we had this declared in the actual module. And then we assign to X the top 4 bits of the count. So that's going from 8 to 5. So our count looks something like that. It has 4 bits from 8 to 5 at the top, and then it has another 4 bits that goes from 4 to 1, and then it has a single bit that's bit 0, and we use that for carry-in. This part here we use for Y, and this part here we use for X. So that's what's happening here with those 3 assign statements. And in this way we feed those into the module that we want to test, and then we produce the outputs S and C out, and we can look at those in ModelSim, for example, in the wave panel. So here are the results that we obtained from simulating this in ModelSim. We have the clock here at the top, and then there is the count. We display this using unsigned decimal integers, using radix 10 and unsigned, so that we can easily read that. Then we have X, and we have Y, and we have S, the sum that comes out. We have carry in, and we have carry out. So for example, here, the first thing on the left, that corresponds to having an X of 0, a Y of 0, and a carry in of 0, and that will produce an output of 0. And then at the next time unit here, or after the next clock cycle of 10 nanoseconds, we now have X0, Y0, but the carry in is now equal to 1. And so we get an output of 1, and so forth. So just as an example, let's go back here. For instance, here we have an input of X equals 1. Then we have an input of Y, which is 0. And we have a carry in, which is a 1. And so that gives us a 2. And that's what we are seeing in here. And we can look at that at other times as well. Here, for example, we look at it towards the end so that we can check whether it goes all the way to adding 9 plus 9 plus 1. So this happens back here. X is equal to 9, that's up here. And then Y in that last one is 9. And then the carry in is 1. And what we are getting is a 9 for the sum, that's over here. And the carry out, that's this part here, is equal to 1. This is C out. So we can see that this one-digit BCD adder is indeed producing the correct results. Now we want to use that one-digit BCD adder to make an n-digit BCD adder. So we have a parameter here, n equal to 4, and we can set that to 2 or 3 or 8, however many digits that we need. The carry input is, of course, just 1 bit, so that's declared here. But then X, Y, and S, they have to be now quantities that can accommodate n 4-bit digits. So we have 4 times n bits in each of those. So those are just vectors with 4 times n bits. The output carry out, that's a single bit. And then we need a vector for the ripple carries. We're implementing this as a ripple carry adder. So we need intermediate places here where we can connect the carry out from one stage to the carry in of the next higher stage. and we need n plus 1 of those. We have n stages, so we have n minus 1 intermediate carries, but then there is the carry into the lowest significant digit, and there is a carry out from the highest significant digit. Then we use a Genvar construct here in order to instantiate the add BCD digit module n times. So we have the Genvar variable I is declared here. We assign at the beginning CC0 equal to Cin, so that's the input to the carry chain. We also assign the carry out to the carry out of the last stage, and then we generate the n instantiations of that add BCD digit module. There is a name here for this that's just called digit, and then there is dBCD, and then each instantiation is going to be called digit.dbcd, and then 0, 1, 2, 3, etc. for each of the values of I in here. So I goes from 0 up to n minus 1, or I less than n, and we increment I by 1 after each instantiation that we make here. And because the input is given in the form of a vector with multiples of 4 for each of the BCD digits, we go from 4 times I plus 3 down to 4 times I with each of those things. So when I is 0, then we go from 3 down to 0 with the indexing, and so we pick out the least significant digit. When I is 1, then we would go from 4 plus 3, that's 7, down to 4 times 1. So we go from 7 to 4, that's the next least significant digit. And then after that, if I is 2, we would go from 8 plus 3, that's 11, down to 8, etc., until we reach the highest one, which is n minus 1, down to 4 times n minus 1, 4 times n minus 2. Okay, so, and we at the end we have to because we use the begin here so that we can have a name for each of those instantiations. We also have to use an end, and then for the generate we have to match this with an end generate, and then of course there is the end module. And to be precise, when I is equal to n minus 1, then we go from 4 times n minus 4 plus 3, so that's 4 times n minus 1, down to 4 times n minus 1 like that, so that's 4 times n minus 4. So that's the last set of indexes that we use for the most significant digit when we run through this generate loop here. Now we're looking at the test bench for that add BCD module, for that n-digit BCD adder. So we set again a parameter here. In this particular case, we have set it to 3, n equal to 3. And we have a clock again, we have a count, but this time we have organized the count a little bit different because we don't know beforehand how long that's going to be, or because we want to make it parameterized, it's a better way to put it. We actually made 4-bit quantities, but we make several of those 4-bit quantities. So we make actually a 2-dimensional array. So we have a count 0, which is 4 bits. And then we have a count 1, which is 4 bits, etc., all the way down or up to count 2 times n minus 1, which is also 4 bits. Okay, it's organized as a 2-dimensional array. And of course, we need 2 times n minus 1 because we need to produce an input for both the x and the y inputs. And so we need if we use 3 digits here, then we need altogether 6 digits that we produce with the count. And then there is a register for the carry input, and we also have a flag that we will use when we are incrementing the counter. Then wire 3 to 0 and n-1 to 0 of those, so that's another two-dimensional array. It's a two-dimensional array of 4-bit quantities, of which we have n altogether, indexed from n-1 down to 0. And that we use to connect to the sum output from the BCD adder. And then we make wires which are just vectors, 4 times n-1 down to 0. So we have 4 times n bits in here for xx and yy, and we have another one of those for ss. And the reason why we need this is even though we produce here our digits in a two-dimensional array, we can actually not pass that two-dimensional array to the next module in Verilog, in this case the module that we want to test, which is the add BCD module. We have to flatten those two-dimensional arrays into a one-dimensional vector for passing it on to the submodule. That's just a feature of the regular Verilog, that you cannot pass on anything more than one-dimensional arrays. And then there is the cout wire, that's just a single bit, and integer k that we use for counting as we go along here, or as an index for counting. Okay, so we do the usual thing. We begin with setting the clock equal to 1, and in this case what we're doing is for the count, we set all the digits in the count equal to 9, so that when the first clock is happening, that all of those are going to go to 0. And the carry in we set to 1, and then when the first clock is happening, that will make the carry in 0. So the initial condition will be that carry in is 0, all the digits of the count will be 0, and the clock will be 0. And we just have to initialize that to the value just before it becomes 0, because the first clock is going to happen at time 0. Then we produce the clock signal, so that makes again the clock signal with 10 nanosecond period. Okay, that's a clock. And then at the positive edge of the clock, we do our counting up. So we increment the count chain by 1, basically. Now this gets a little bit complicated because we again have to avoid using digits that are not legal BCD digits, because we don't want to feed those into our adder because it's not designed to produce the right result for those kind of things. And so what we do is as a first thing, when we see the positive edge of a clock, we toggle the carry in. So we use the carry in as the least significant bit, so that will go 0, 1, 0, 1, 0, 1 for each of the clock cycles. And then when the carry in is equal to 0, then we also increment the counter, which counts the BCD digits that we use for the inputs for x and y later on. Okay, so we set the flag equal to 0, and then we go for k equal to 0 up to 2 times n, actually 2 times n-1. And if the flag is 0, then we increment the corresponding digit in the count. So we start with the least significant digit and add 1 to it. If that digit stays less than 9, or less or equal to 9, then we set the flag equal to 1 to tell the follow-on digits that we do not need to increment them. If we reach something greater than 9, which is typically 10, in any particular digit, then that means that we now have a rollover for the next digit. So we then bypass this if count k is less or equal to 9, so then count is greater or equal to 10. And so we bypass that, and then we go back and increment the count here again, because the flag stays at 0. But And when we do the rollover, we also have to set the current digit back to 0. So we go from 9 back to 0, and we create essentially a carry or a rollover for the next digit using this construction here. The reason why we need to use that construction with the flag is because Verilog does not have a break statement. In C language, for example, you can do a for loop, and then you just give a break statement when you want to exit the for loop before you have gone through all of the fors. In Verilog, in the regular Verilog, you cannot do that. And here is the second part of that test bench. We now need to actually flatten those two-dimensional arrays and make those into one-dimensional vectors in order to pass them to the module that we want to test. So we have the counts over here, and we use again a generate construct. So we use the upper n digits in the count array for x, and the lower n digits we use for y. So we have here the upper n digits, and here we have the lower n digits of count, and those get assigned to x and y. And remember, we had 2n digits, or an array with 2n 4-bit quantities for the count, so that we have n of those for x and n of those for y. And then we also assign to Si, that is the two-dimensional array, we assign the corresponding 4-bit slices that we get back from the testing of the adder, and we get that back in the form of a vector, of a one-dimensional vector as well, and we make that back into a two-dimensional array, which is the Si array. And finally, here is the actual module that we want to test, the MUT, the add BCD module. So we have the carry in that gets toggled during each clock cycle. Then we have XX and YY that comes from the count. And we have SS, which is the sum, that is the BCD sum that's being computed by the module. And we have Cout, the carry out that comes back. And we also have to define the parameter of that module under test to make it equal to the parameter that we are using here in the test bench. And we do this by using the def param mut.n being equal to n. So mut.n refers to the n in the add BCD module, and the black n in here, that refers to the n that we have been setting in that test bench. Okay, and here is once more the statement about what XX and YY is. So XX is the vector from the top n digits of count, and YY is the vector from the bottom n digits of count. And once more, the reason why we need to do this is because in regular Verilog, you cannot pass a two-dimensional array to one of the submodules that you use. You have to make it into a one-dimensional array, which is called, you're flattening the two-dimensional into a one-dimensional thing. Here are the results of using that test bench with n is set equal to 2. So we produce all the numbers going from 0, 0, 0 plus 0, 0, 0 all the way up to 99 plus 99 plus 1. The 1 here is the carry in, and we check whether we get the right results. And what we are seeing here, for example, is the leftmost one, this one here, is an input of 67 plus 29. So that gives us basically 67 plus 30, so that's 97, one short of that, but because the carry-in is equal to 1 here, we actually do get that 1, so we get for this particular entry here 67 plus 29 plus 1, and that gives us 97, so that looks right. If we look somewhere here in the back, for example this one, that would be 67 plus 38 plus 1. Okay, so that gives us 67 plus 38 is 105, plus 1 is 106. So we see the 106 here, and we also see that for the carryout, that this is equal to 1. And so that means then that the result is 106, and that looks correct. So now there is a little catch here. Even if n is only 2, exhaustive testing requires 100 times 100 times 2, 20,000 simulation steps. Okay, that is actually going pretty fast in ModelSim. But if we increase this now for n equal to 3, then we have to run 2 million simulations. And if n is, and that actually takes an appreciable amount of time. And if n is larger than 3, exhaustive simulation of going through all possibilities of the x and y inputs and the carry-in inputs is not very practical anymore. At some point, ModelSim will just refuse to do this many simulations, or if it wouldn't refuse, it would just simply take too long for it to reach the end of the simulation. And so what we do then is we can make another test bench where we are just testing specific cases. And the way we go about doing this is we are now not producing a clock anymore. We just simply use an initial statement and put our different cases in here. But of course, we have to define things like the parameter. So here we chose a parameter n equal to 4. The cin is still a 1-bit quantity. We use, again, 2-dimensional arrays for x and y, not in the form of count anymore, just as a separate x and y array. And we have a 2-dimensional array for the s output. So those are, again, arrays that contain 4-bit quantities. And if we set the parameter, or if you look at the parameter n here, we produce n of those 4-bit quantities. And then we will again have to pass on those 2-dimensional arrays in the flattened form, in the form of 1-dimensional vectors. And so we define here wires for xx, yy, and ss in the same way as we did this before. So those are 4 n-bit quantities. And there is also a wire for the carryout that we receive back from the adder. And now we just, in an initial statement, we just simply write what cases you want to test. So the first case here, so this is the first case. We are testing 4,288 for the x input and 3,046 for the y input. And the carry-in we specify to be 1. Then we delay things by 10 time units so that when we look at the wave display in the end, that we can distinguish our results nicely. For the second case, we chose to set x equal to 6,975, y equal to 8,537, and the carry-in of 1. And then there is the third case. So here we have a 0 for the most significant digit of x. So we have 196 plus 1,502 plus 1. And the last case is 7,027 plus 1,991, and the carry-in of 0. There was no particular reason to choose exactly those numbers. We just simply generated a bunch of numbers at random and then used them for this test. But sometimes there are corner cases that you would like to test. For example, you could test whether 99 plus 99 plus the carry indeed gives you 199 and not 200, for example, or not 198. Or you could test whether 50 plus 49 does not produce a 100th digit, whereas 50 plus 50 should produce a 100th digit. And then the second part of the test bench, we have to again convert from the two-dimensional arrays, which are the x, y, and s in here. So those are this one here, this one, and this one. They come from the two-dimensional arrays where we store 4-bit quantities in the two-dimensional array, and we have to convert those to one-dimensional vectors or flatten the two-dimensional array for feeding it into the module under test, which is down here, or for receiving it from the module under test and making it back into a two-dimensional array. And of course, there is the carry in and the carry out that need to be assigned as well. And we have to set the parameter again using the def param mut.n equal to the n of the test bench. And if we are running this, we get the display that looks like this. And we can see here in the display that we are looking now at those test cases. So we have 4,288 plus 3,046. And the carry in, which is up here, is 0 in this case. And so we add 4,288 plus 3,046, and we find this is 7,334. And that is the result that we are seeing down here. And similarly, for example, so here is the second test case. The third test case, if you look at this one, we have 196 plus 1,502. And in this case, the carry-in is 1. So we add a 1 for that, and we find that this is 1,699, which is the result that we see down here. And so we can verify for those 4 test cases that we indeed get the right result. A variation on this would be to not by hand come up with specific numbers for the input, but to generate those at random. And there is a command in Verilog where you can produce random quantities for the purpose of testing things, but we have not implemented this for this particular video.